don't have your test graded yet. Maybe by Friday I'll have them done. Okay, this is kind of where I'm going towards Lewis structures for molecules. There's a few things to discuss on the way, but just to refresh your memory, this is kind of the way I have a roadmap of the way I go through this. I've said this before, there's ionic compounds, covalent compounds, metallic, and something called those are the four types of compounds throughout the entire universe. We've already talked a good bit about these. We'll come back and do some ionic reactions later. But we talked about these ionic compounds. We practically have not talked at all about covalent compounds, but this is where we are. This is where we are now. These we don't talk about much. They come up in very specific small places, and these we don't talk about at all. In some sense, our semester is about this. It's really about ionic and covalent compounds. And I haven't done hardly anything on covalent compounds. Only naming them like carbon tetrachloride or phosphorus trichloride or something like that. Now we're going to actually talk about what covalent compounds are. And another thing to say is, for ionic, and this is where the name comes from. Ionic bonding is what brings together ionic compounds. For instance, ionic bonding tells you that it's the charges that brings them together. The positive, negative charge pulls them together. That's ionic bonding. That's what ionic bonding is. And if I wanted to tell you what the structure of, NaCl is table salt, if you dumped out some table salt, you see the compound laying on the counter. The structure of NaCl is this. And then right below this Na, I'll put a Cl, Na, so I'm just alternating. Okay, so I'm alternating sodium, chlorine, sodium, chlorine, sodium, chlorine. And then across, I'm alternating sodium, chlorine, sodium, chlorine, sodium, chlorine. But now picture just in front of this sodium atom, a chlorine atom right here, and then a sodium atom here, and then a chlorine atom here. So really this is just a huge three-dimensional array, huge compared to the size of atoms. I mean, if you look down at one little grain of salt down on the counter, it's basically a chunk of that. So we call this a lattice structure, or an array. You know what I'm saying? That's, ionic structures tend to do that. So it's always this alternating system of positive and negative ions. Does that make sense? Talk a little bit more about this structure later in this semester, but molecules, what we call molecules, this is, of course, so now we're talking about covalent bonding. And if I just gave you, I'll just go, there's an example of a molecule. So you have this, and if I had a big sample of this, I would have this, and then along with it, I would have one of these, and another one of these. So, in some sense, when it comes to ionic compounds, the little, if you zoom in real close and you look at what is this made up of, it's made up of all these ions in this perfect array. When you look at a covalent compound, you just have a bunch of these molecules jumbled together, I should say. Covalent compounds, this is where we talk about molecules. Where you have this little unit, and then you have this little unit, and you have this little unit. So if you look over here and you said, what is the formula you would use to represent this? Overall, it's a 1-to-1, like for any sample of this you have a 1-to-1 ratio here. So we would go one Na to 1 Cl. Over here, the unit formula we use is just one of these. We can call this CH4. So here, this formula is really representing the molecule, whereas here the formula is really representing the ratio of the atoms. Just to backtrack a little bit, what if we had two? So now we've got Mg2 plus and Cl, and this is a subject you'll cover in 1212. So something like this is kind of hard to do. Let me just do it like this. So you have that unit, you have that unit. This is kind of hard to do in a way, but there's a specific three-dimensional way that you can get this ratio going on. So if you looked at this overall chunk and you made that big array, you would be looking at for every 2 Cls, there's 1 Mg. So this is, again, the ratio of any given sample. So the array isn't quite as nice and neat as sodium chloride, but you can do this with any of the charges. It's just one little unit is going to have one of these and 2 of these. So this is really representing ratios. Whereas when it comes to molecules, we always just give the listing of the molecule in the formula. So this is literally the representation of this. This is like a summary form of this. So there's the formula. We sometimes call this the structure. Somewhere in between, there's something called a structural formula. But I won't harp on that. But this is where we are now. We're going to talk about molecules. Okay, the first thing is you need to be able to identify the number of valence electrons for any given atom. So first I'm going to talk about, let me erase this. we're talking about this is where we are. And specifically Lewis structures for atoms and molecules. Should put that here. So here's where we are. So we tend to use these things called Lewis structures to represent the molecule. Valence electrons. So I'll bring this up on the screen, but if you just look at your periodic table, valence electrons, the simple description is, if I said, how many valence electrons does oxygen have? You put your finger on oxygen and you start counting to the left. 1, 2, 3, 4, 5, 6. Oxygen has 6 valence electrons. So does sulfur and so does selenium. Everything in that column all have 6. If I did fluorine, it would be 7. I would count fluorine. 1, 2, 3, 4, 5, 6, 7. You follow me? I'm going to focus mostly on nonmetals because covalent compounds are made up of all nonmetals. So I'll focus mostly on these. But quick description. So the column with fluorine in it, fluorine and everything below it, 7 valence electrons. Oxygen and everything below it, 6 valence electrons. Nitrogen is 5, everything below it is 5. Carbon is 4, boron is 3. So it is that simple. You can just look at a periodic table and count, or you can memorize what I just said. All right, so if I say give me the valence structure, let's do, we've got hydrogen, I'll do boron just for an example. And I'll do those two. Chlorine, bromine, sulfur. Should I do, well, I'll just include just so I have something of the periodic table in front of me. Noble gases. All right, I'll just, so all nonmetals. Boron is a metalloid, but I'm still going to keep it there. There's nothing to do with that yet. So here's the Lewis structure. Lewis structures, sometimes they're called Lewis dot structures. Sometimes they're called dot structures. Sometimes they're called Lewis structures. Sometimes it's called the Lewis symbol or the dot symbol. But here's what I'll call the Lewis structure for nitrogen. How many valence electrons for nitrogen? What'd you say? It's 5. Here's how you make the structure. This is very simple. You just go around, you go 1, 2, 3, 4, and now that I'm coming back around, I'm going to pair it and say 5. That's the Lewis structure for nitrogen. Let me do oxygen. How many valence electrons for oxygen? It's 6. You go 1, 2, 3, 4, and now I'll start pairing them 5 and 6. That's the Lewis dot structure for oxygen. It is that simple. I should also mention, notice I have a pair of electrons there, a pair there. Sometimes we say lone pair. I don't know why we say lone, but pair of electrons, and these are single individual electrons. Let me point out that the correct Lewis dot structure for oxygen could also be written like this. It could also be written like this. The whole point is, when you're done writing the Lewis structure for oxygen, there should be 2 pairs of electrons and 2 single electrons. When you're done with nitrogen, there should be a pair somewhere and then 3 singles, meaning this is a perfectly legitimate Lewis dot structure for nitrogen as well. I usually just start at the top and start going around, so I end up with these. But just to point out, these are correct too. The point is 2 pairs and 2 singles. Here, 1 pair and 3 singles. Right. Nitrogen, oxygen, I'll put carbon here. How many for carbon? 1, 2, 3, 4. Now go on out to fluorine. Fluorine is 7. 1, 2, 3, 4, 5, 6, 7. So there's a Lewis structure for fluorine. I'll do neon as well. Neon will be 8. If you count around, you'll go 1, 2, 3, 4, 5, 6, 7, 8, which means they're all pairs. The octet rule. Chemistry books love that word. The idea is, if you looked at all of these and you said, okay, I want 8 electrons around each one of these. Neon already has 8, so octet rule, this one's following the octet rule. If I brought in another electron to fill up the octet around fluorine, then I would have this. So a week ago, if I asked you what is the charge on the fluorine ion, you would count 1 to the right and you would go charge -1. But this kind of shows you how that happens. For this to fill up its octet, if you take 1 extra electron and pair it up right here, then you would have -1. That's what the fluorine negative ion is. Same with oxygen. If I ask you what's the charge on the oxygen ion, you would say 2 negative. That's because it tends to fill up this octet. You get an extra there and an extra there, and then you would have 2 minus. Nitrogen, you would say -3. If carbon rarely shows up as an ion, but when it does, it's going to be -4 because you pair all of these and you'd be -4. But getting away from ionic compounds and sticking to covalent compounds, here's what you can find out from these Lewis structures. You know what it is? So, neon doesn't tend to ionize because it's already got a full octet. Fluorine will ionize because it's got 1 more space for an electron, so it can be -1. So I realize I'm going back and talking about ions, but I want to contrast some. Oxygen can get 2, nitrogen can get 3 extra electrons, making it -3. But that tells you why neon never shows up as an ion. Therefore, it never shows up in ionic compounds. We call these de novo gases. And we usually say they're inert, meaning they don't undergo chemical reactions. Well, this is a hint why this wouldn't be involved in an ionic bond. As in, it's inert, it won't make bonds because it's already got its full octet. This will show up in ionic bonds. It's not inert because it can gain that extra electron, and then it's negative. Then it can be attracted to something positive and form an ionic compound. Okay, contrast that with molecules. So here's what covalent means. Covalent. It means, let me just show you an example. Here's oxygen. Do it like this. Hydrogen, how many valence electrons does it have? It actually only has 1 electron, period, so that has to be its. If I did the Lewis structure for hydrogen, you would count to the left and you would go 1, so you would just have 1. That's the Lewis structure for hydrogen. Here's the point. There's the Lewis structure for oxygen. Here's the Lewis structure for hydrogen. This is H2O that I'm making. It's the sharing of electrons that is what causes the bonding for covalent molecules, for covalent compounds. Meaning these two electrons, they pair up. These two electrons pair up. And that's what causes the bonding. Not positive, negative charges pulling things together. It's this tendency of electrons to try to pair with each other. So if this hydrogen was floating near this oxygen and this hydrogen was floating near this oxygen, they would have a tendency to click their electrons together to form that covalent bond. That's what this line represents. The line represents two electrons. One of them came from hydrogen, one of them came from oxygen. That's what a covalent bond is. It's this tendency of electrons to try to pair up that causes molecules to occur. You follow me? Okay, so here's what you can get by making these Lewis structures. How many covalent bonds will fluorine make? One. It's only got one unpaired electron, so this can make one bond. And I mean here covalent bond, not ionic. How many bonds can oxygen make? It's obvious just looking here. There's two unpaired electrons, so two bonds. Oxygen pretty much always makes two bonds. Nitrogen, how many bonds will that make? This will make three bonds. How many will carbon make? Okay, and when we talk about covalent compounds, aka molecules, we're mostly talking about, we're pretty much always talking about the nonmetals. And if you just want a complete list, because there are not that many nonmetals, they're all in that top right corner. Oh, hydrogen is a nonmetal. How many bonds will it make? It's only got one of these, so it's one bond. And then if you went to silicon just below carbon, and you did its valence structure, it's going to look just like carbon. And phosphorus below nitrogen, anything below nitrogen, is also going to be just like nitrogen. So there's the Lewis structure for phosphorus, and it will make 3 bonds. Silicon will make 4 bonds. Same for anything below oxygen. Sulfur looks just like oxygen for its valence electrons. So it will make 2 bonds. Chlorine, bromine, iodine, going down here, those will always make 1 bond. And of course, anything below here will make no bonds because it has its full octet. It doesn't have any single electrons floating around. So it won't make covalent bonds either. This won't make ions. This whole column won't make ions, so it doesn't get itself involved in ionic compounds. And it has all its electrons paired, or all of its valence electrons paired. So it can't make these covalent bonds. So that's just sort of the description why the noble gases are inert. They don't get involved in these chemical reactions that everything else does. Okay. Lewis structures for atoms, and I also described valence electrons. And what you get from this is how many bonds can something make. So that's kind of the first thing to bring up when it comes to Lewis structures. You can do Lewis structures of ions, and I'll involve some metals here, but if you wanted to do the Lewis structure for let me look again. said, give me the Lewis structure of sodium, sodium has one valence electron. Electrons are negative, and a week ago if I asked you what is the charge on a sodium ion, what would you say? +1. Metals tend to lose electrons, so it's going to lose this electron to become positive, so there's nothing around it, so that would be the Lewis structure for sodium. It's kind of a moot point, but it's the non-metals that you can actually do something with, like oxygen was this. That's neutral oxygen. If it gains those 2 electrons, then it shows that full octet. Now that's 2 molecules. So that would be the Lewis structure for oxide ion. It's got those 2 electrons in there in a full octet. You with me? Mostly though, I want you to focus on the neutral atoms. But that's all right. So you guys can look at those. But it is that simple. So I want to go to chapter 5. There is this set of rules. So starting in chapter 5 and section 5.3. It gives you a system of rules to follow to make Lewis structures for molecules. But let me just come up with some examples without following these rules to give you an idea. If I said, there's the formula, give me the Lewis structure of carbon tetrafluoride. One thing you could do is you could start with, just on the drawing board, do that, and then there's 4 fluorines, and they're all going to be, let me split them up a little. So these are the ingredients to this molecule. And fluorine, if you make the Lewis structure, you'll end up with this. 3 pairs and then 1 single electron by itself. So there's the ingredients, and I got to stick these together with covalent bonds. So one strategy would just be write down all your ingredients, all of these, put in the valence electrons, have the dot structure. How many bonds can carbon make?
4.
Makes 4. How many can each one of these fluorines make?
1.
So it's kind of obvious how these go together. It's like I ask my students this every semester. Have you ever heard of Tinker Toys? And everyone has. That astounds me, but Tinker Toys are still around. You guys know what I'm talking about? Something you play with as a little kid. It's like they have sticks and little blocks of wood and holes in them and you can stick them together. Maybe they're called something different now. Yeah, anyway, it's kind of like that. You look at this and you go, there's 4 here, and each of these with 1, you can kind of figure out that the overall structure is going to be this with 4 S sticking off of it. There's really nothing else you can do here. If all of these need to go together in a molecule, and you first start off by trying to do this, you look at 2, 4, and you go, hey, I can make a bond. Yeah, you can do that. But that's it. You can't stick anything else to that. So that'll be a molecule by itself. So you immediately go, okay, I guess I can't do that because I've still got to accommodate these fluorines and that carbon. If you stare at this long enough, it's just obvious. The only way you can do this is for the fluorines to be on the outside. Fluorine, fluorine. Pair those two, you pair those two, you pair those two, and you pair those two. That's the Lewis structure for CF4. So if I gave you that, and I said, can you come up with a structure, that's the only structure you could make. It's the only possible way to get these 5 atoms to stick together, given the rules. You with me? So without following the formal rules to make a Lewis structure, just sort of the reasoning is this. That's how these all stick together. That idea about the octet rule, so this fluorine by itself, and here was carbon, this one is not following the octet rule. It needs an extra electron. Carbon is not following the octet rule. It needs 4 extra electrons. Over here, let's check this up a little. It should look a little more symmetrical. So over here, they all achieve the octet rule. They're just borrowing from each other. Fluorine wanted to have 8 electrons around. It's got 2, 4, 6, and it had 7, but by grabbing onto this one and sharing it with carbon, it in some sense now has 8 electrons around. So that's fluorine following the octet rule when it goes into carbon. Same with carbon, it's cheated by borrowing one here, borrowing one here, borrowing one here, borrowing one here. Now it has 8. There's 2 electrons in each one of these lines. So now carbon has 8 electrons around it. So now carbon has achieved the octet rule as well. So that's the idea. But typically you're given, you start by writing the correct skeletal structure for the molecule. I think that's the hardest part of this, although it's a little tedious just in general. But I'm typically okay with, say for a test, giving you the backbone, what I call the backbone, skeletal structure, backbone, I tend to say backbone. But the skeletal structure would be like, if I did CF4 again, what if I gave you and I said, take this backbone structure, this skeletal structure, and finish out make it into a full Lewis structure. Lewis structure just means all the electrons are also there and all the bonds are all there. Then you would follow this formal set of rules because these can get larger and more complicated. I need to go. Before I start doing those rules, let me show you one more twist. Let me do CH2O. So you've got oxygen, you've got 2 hydrogens, and you've got carbon. And without giving you any rules to follow, let's say it's this, and you still got something to do with these two. Let me start again. I'll go ahead and place these atoms kind of where they need to be. Okay. Hydrogen with its 1 electron, hydrogen with its 1 electron. Oxygen with its 2 pairs and its 2 lone electrons, and then here's carbon with all 4 of its unpaired electrons. All right, if I started connecting these up, I can do that. So carbon has gone from having 4 electrons to now having 6 around it. Hydrogen doesn't follow the octet rule. I'll come back to that. And then I can definitely make a bond there. But these need to be paired too. For you to have a molecule, you have to have all the electrons paired. So I can take this electron and swing it over here, and take this electron and swing it up here, and make one more bond. Now I've made a double bond. These are what we call single bonds, and this is a double bond. Now, what I've achieved is all the electrons are paired, And all my atoms that do follow the octet rule are now following the octet rule. Oxygen has these 4, and it gets to count both of these. Those 2 in this line and the 2 in this line, so now oxygen has 8. And now carbon has 8. There's 2 electrons in this line, there's 2 electrons in this line, 2 there, 2 there, now it has 8. But hydrogen doesn't follow the octet rule. I'll come back to that. But that's what we call a double bond. And let me show you one more that's an example of a triple bond. Come over here. You might see that sometimes it's written as, and sometimes it's written like that. But I'll get to how you look at the formula and decide what goes where. But if I had this, and let me make the, I've got nitrogen. If you were just trying to reason your way into what would the structure be, you can look at this and go, carbon makes 4 bonds, nitrogen makes 3 bonds, hydrogen makes 1 bond. You don't have to think too long before you realize 3 of the bonds from carbon are go to the nitrogen, and the last bond from carbon will go to the hydrogen. If I just sort of started the molecule, nitrogen, I'll put the pair on the right side. I'll go, okay, I can pair those. So now that's attached. I can pair these. Now that's attached. That's what I would call the, no, that's not the skeletal structure. But anyway, I can swing this electron up here, this electron up here. You get them to pair, and then swing this electron down here, swing this electron down here. Get them to pair, and now you're looking at a triple bond. And that's it. There's no quadruple bonds or anything else. There's single, double, and triple, and that's it. There's no more than that. So between 2 atoms, you can have 1 bond made up of 2 electrons, or between atoms, you can have 2 bonds made up of 4 electrons, 2 per bond, or between 2 atoms, you can have 3 bonds. But no more than that. Okay, so there's such thing as double bonds and triple bonds. And that's kind of one of the reasons that Lewis structures start to get a little more complicated. In which case you'd like to have a set of rules to follow. I think that's enough. That's enough logic to sort of draw us in now. Skeletal structure. Okay. Let me go to these examples. Exercise 27, 28. Let me pluck one of these out to use. Again, these are all nonmetals from the top right of the periodic table, and hydrogen. Let's see some of these. This is from 30. I'll use those as examples. Okay, these rules. So the first rule is about which atoms are central and which atoms are terminal. For instance, H2O. You could draw the Lewis structure for H2O like that. It's also perfectly legitimate to do it like that. But the point is here is these are terminal atoms and this is a central atom. And determining what's central and what's terminal is really kind of your first step. If all you've got is a formula, you have to figure out what goes in the middle and what's out on the edges. Don't worry about that exception for B2H6. But I tend to like to give you the backbone structure and you start with that. But these questions in the book you have to figure out. But in general, the rule is, unless it starts with hydrogen, the central atom is the one it begins with. So this is going to be central. This one will be central. One of these carbons, actually both of those carbons will be central. That's central. Nitrogen is the central. And like I said, unless it starts with hydrogen, if it starts with hydrogen, go to the next atom in on the formula. And that generally almost always works. But I don't want y'all to be hung up on figuring out what the backbone structure would be. But if I did NF3, I would go in, and then, and I would call that the backbone structure. Neaten it up a little. So let's say you started with that. That takes care of rule one. Get the skeletal structure. I tend to call this backbone. It just depends on which book you're using. This involves so I just made a single bond there, a single bond there, a single bond there, and I call that the backbone structure. Given that this is the Lewis structure of nitrogen and this is the Lewis structure of fluorine, it's really kind of obvious where all the electrons go here. But let me follow these rules because the bigger the molecule gets, the more you want to rely on these rules rather than just sort of the simple logic you do. Obviously, this makes 3 bonds. Fluorine makes 1 bond. Assume you've already been given that. So it's kind of obvious how this goes together if you just think of them as tinker toys. But your second rule, these rules are very wordy. Calculate the total number of electrons, valence electrons. So I would do it like this. Nitrogen has how many valence electrons? 5, and there's only 1 nitrogen there. So you get 5 electrons, valence electrons from nitrogen. Fluorine, how many valence electrons? 7. And there's 3 of them. You add them all up and you get 26 electrons. So that's what I was after, that number 26. Rule 3, add electrons to the structure, filling the octet, but you start with the terminal element. I have 26 electrons. I need to fill the octet for the fluorines. This fluorine already has 2, so it just needs 6 more. 2, 4, 6. Now that fluorine has a full octet. I've used 6. Oh, hold on. I guess there's a rule that goes here. So I started with 26. Let me back off this. So I've got 26 valence electrons to work with. But just to make this skeletal structure, I've used 2, 4, 6. I've already used 6. So really I have 20 left to play with. So you do have to include those single bonds you use to get the skeletal structure pasted together. All right, so now I'm here where I fill the octets. Start with the terminal atoms. So I'm going to go, this fluorine already has 2, so it needs 2, 4, 6 more. Now I've got 14 left. 2, 4, 6, 8, 10, 12. Minus 12, so I'm down to 2 electrons. Now that I've filled the octets, if any are left, then you put them on the central atom. You can read those rules. They're a little more wordy. This may not be the most complete way to say this. But I've got 2 left. I'm going to put them as a pair on nitrogen. And now I'm done. I'm down to 0, so now I'm done. The more complicated ones of these, there's more to do than that, but this one is nice and simple and it's all done. What I'm looking for is the full octet on all the atoms. If I follow these rules, once I get a full octet on all the atoms, I can stop there. That's the Lewis structure for NF3. But like I said before, don't lose your tinker toy logic. If you knew this much about the atoms involved, you could probably figure out the structure without following these formal rules. So don't lose your intuition. If there's 3 of these and 1 of these, there's really kind of only one way to put these together. It's when double bonds show up and triple bonds show up that it gets more important. Let me do one. Let's do SBR2. Let's do C2HO. I wrote that down wrong. CH2. CH2O. Actually did this one before, but it'll be good to follow these rules. So now you're given and you'll do carbon is central. Single bonds to connect everything. That's what I would call the skeletal structure here. All right. All right. Following the rules, we're here, and we would go hydrogen, there's 2 of them, oxygen, there's 1 of them, carbon, there's 1 of them. Hydrogen has 1 valence electron, oxygen has 6, carbon has 4. I've got 12 valence electrons to deal with. All right, I've got 12 valence electrons to work with. I have already used 2, 4, 6, so really I only have 6 left. Of the atoms, of the terminal atoms that do get an octet, it's just oxygen. So I'm going to add electrons to the oxygen to give it a full octet. It's got these 2 already. So 2, 4, 6. There, I'm done with that. So now I'm at the 4th group. The problem is we don't have a full octet everywhere. Go back to the rules. So we managed to get to rule number 3, distribute electrons among the atoms given octets. It's a duet in the case of hydrogen. All right, rule number 4, if any atoms lack an octet, form double or triple bonds as necessary to give them octets. The problem here is carbon doesn't have an octet. So what you can do is borrow a pair from out here and make a second bond to carbon. I'll just grab those 2 and turn them into a bond. And that does it. When I take that pair of electrons and put it here, it doesn't take it off of oxygen. Oxygen is still pretending all of these are part of it. So oxygen has 2, 4, 6, 8 around it. Carbon only had 6 around it. And it needed to have 8. So I borrowed that pair. Now carbon has 8. Now oxygen has 8. Now that everything has its octet, we're cool. And that's the Lewis structure for that. CCl4, let's do CCl4. C2Cl4. So do carbon like that, and I know it's not really, they don't really give good rules on how you would distribute these. Like I said, I will tend to give you a backbone to start with. So there's the backbone that I would give you to start with, say on a test or something. So if we follow these rules now, we've got carbon, we've got 2 of them, we've got chlorine, we've got 4 of them. Carbon has 4 valence electrons, chlorine has 7. This is 28. So we have a total of 36 electrons to work with. 36 electrons. 2, 4, 6, 8, 10. We've already used 10 just to make this backbone structure. All right, so now we will fill the octets of the terminal atoms. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All the chlorines have their octets now. We've got 2 electrons left. We got to put it on one of the 2 carbons. We put them on as a pair. I'll just put them there. So there, now this carbon has its octet, but this carbon still does not have its octet. The way you solve that is, in one fell swoop, you do that, and now this carbon has its octet too. That would be the Lewis structure of this. The twist here is you have to form a double bond between the oxygens. Again, I think you could use Tinker Toy logic to figure this out. But these formal rules get more important, the more complicated things get. So let's do. Let me look again. What have I signed? Those. Okay. And we don't have very good. Let's do, okay. CN, that's one of those polyatomic ions. We call that one cyanide. I did mention when we were talking about ionic compounds, there is such thing as polyatomic ions. I'll give you a list of them. The polyatomic ions are actually covalent compounds. They just happen to have an imbalance of electrons, which gives them this charge. So if you did CN, the backbone would be just be that. But when we do this, we've got carbon that has 4 valence electrons. We've got nitrogen that has 5. That's 9 electrons. But this charge here tells you there's 1 more electron. If this was 2 negative, I would need 2 more electrons. If it was 3 negative, I'd need 3 more electrons. That negative charge tells you you need to add 1 more electron to this to get a 10. So this tells me I have 10 valence electrons to deal with. So if I've got 10, and I've already used 2 to do this, now I've got 8 left. You could just do this on either one of these because there's not a central atom or a terminal atom, but I've got 8 left to work with. Let's say I went 2, 4, 6, 8. I could have done this, 2, 4, 6, 8. But the point is, in this case, nitrogen has its octet, but carbon does not. Carbon only has 4 around it, these 2 and these 2. Carbon needs 2 more, so you just do this. And that's the Lewis structure for this. And you do the same logic here. You go, nitrogen still needs 4 more, so you would just take those 2, take those 2. You end up with the same structure. It doesn't matter where you put these pairs. You tend to see them written more symmetrically like that. But it's correct either way. That's still the Lewis structure of cyanide. Oh, and I have to add this. Put the charge on there like that. You put brackets around it, and then you put this charge on the outside. Should I do 2? I think I can do NO2 without adding too much. NO2 negative. Let's do CO3 negative. CO3 2 negative and ClO4 negative. series of, okay, let's look at the periodic table again. What periodic table? Okay, this thing about octets, I think it's kind of overemphasized, but let me give you the logic here. If you start with hydrogen, and I said, okay, give me the Lewis dot structure, and I ask you, is this going to follow what we call the octet rule? Well, it can't follow the octet rule because it only has one electron. It's got to have at least an electron in all the four spaces around it before it's going to be able to get an octet. So hydrogen and helium do not follow the octet rule. Neither does lithium or beryllium. Boron can't either because it only has 3 valence electrons. I mean, boron.
Is that because of the orbitals? Or no?
I wouldn't say the orbitals because there are some exotic cases where those extra orbitals do get filled up in boron. But if we just stick with the Lewis structure logic, there's boron. And if I said, give me the Lewis structure, you would do that. And the problem is there's not even a pair of electrons that would pair here. So boron does not follow the octet rule. And then we get to carbon. These all do follow the octet rule. And then if I continued out and I said, okay, here's the rest of our nonmetals. Starting with phosphorus and anything bigger, including these can have what we call that it can have more than the 8 around the central atom. That's the twist that shows up in the more complicated molecules. Let me just pull one up. The more simple way to put it is, those are the atoms that follow the octet rule, which is why the octet rule is kind of silly, because there's only a tiny number of atoms that really follow it. But that's a simple way to put it. Those will always follow the octet rule, the ones I've got here. And starting with phosphorus and anything bigger, including going down the periodic table, go back to the periodic table. Starting with phosphorus, atomic number 15, and just looking at the rest of the nonmetals down here, it's phosphorus, sulfur, chlorine, argon, and anything else down below here can have what we call an expanded octet. It can have more than 8 around the central atom. So it's kind of silly to call it the octet rule when a small number of the nonmetals actually follow the octet rule. Boron is a metalloid, but it shows up in a few molecules, so I'll include it in the discussion. Hydrogen doesn't follow the octet rule. Boron doesn't either. Carbon, nitrogen, oxygen, fluorine, and neon do follow the octet rule. And then when you get down here to phosphorus, silicon is a metalloid. But phosphorus and any of these down here, these can have an expanded octet. There are even atoms that have covalently bonded xenon. I did tell you that these were inert and they never get involved in bonding, but there's always exceptions to the rules in chemistry. So let me do PCl3, and I'll follow these rules, and you'll see where the expanded octet shows up. I would just say refer to the book for the rest of these rules, because they're too wordy for me to put them up here. See the book. Okay, PCl3. Give me the Lewis structure for PCl3. You can start by this and going, okay, hydrogen's not first. It's got phosphorus first, so that's going to be the central atom. And then you just draw single bonds to the 3 chlorines. So you start with that. Okay, 7 valence electrons for chlorine, There's 3 of them times 7, 21. You've got 1 phosphorus. It's 5. So we have 26 total electrons to work with. 2, 4, 6 we've already used. So we're down to 20. Now we start adding electrons on the terminals. 4, 6, 18. This one isn't going to do it. PCl3. That's 2, 4, 6, 8, 10, 12, 14, 16, 18. This isn't going to do what I wanted to. I've got 2 left. I put them in the central one. Now everything has its octet, and I didn't end up doing what I thought I was doing. What is it? PCO. Okay, yeah, PF6 is up there. Let's use this. As usual, the book doesn't have all the examples I wish it had. Okay, let's say you were given that. It's got a negative on it. Phosphorus, there's 1 of them. F, there's 6 of them. And I'm going to say plus 1 more electron. So 1 more because of this negative. So we end up with 48 electrons. 47, 48 electrons. All right. The backbone here . So obviously phosphorus doesn't have just 8 electrons around it. 4, 6, 8, 10, 12. Maybe this isn't going to do what I want it to either. Six. 2, 4, 6. No, we're just going to end up. So you do see the expanded octet, but I don't have to add any more electrons to the phosphorus. But clearly phosphorus has more than 8 electrons. But you managed to get that just by making this the central atom and these on the terminal. Look again at these examples. I'm probably going to have to borrow from materials from another class because this book is so So that's 28 plus 6. 4. I think SF4 will do what I want it to. Say you were given SF4, and that's going to be valence electrons is 4 times 7 is 28, plus 6 more, 34, and then that's if I just did that right, then this will work. So you just do this. There's your backbone. All right. 34 electrons. 4 times 7 is 28. Plus 6, that's 34. 2, 4, 6, 8 we've already used. 34 minus 8 is 26. So I've used 2, 4, 6, 8 just to make this backbone, so I've subtracted 8. Now I've got to fill the octets on the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right. I've got 2 electrons left, but everything has its octet. So we're going to put this pair starting at, bring up the periodic table again. Starting at phosphorus and anything bigger, anything larger atomic number than phosphorus in the non-metals can have the expanded octet. So it's okay to put more than 8 electrons around sulfur. So the pair of electrons will go here, just squeeze them in. That's the Lewis structure for SF4. So just realize if that central atom is phosphorus or larger, higher atomic number, you can put more than the octet on that central atom. And that's one of these rules that shows up down here. When everything has its octet, but you've got leftover electrons you've got to put somewhere, you stick them on the central atom. That's really important for molecular shape, when we get to molecular shape, and that's coming up. Those of you who took chemistry before, do you remember molecular shape? You don't remember doing that at all? Are you shaking your head because you hated molecular shape? A lot of people hate molecular shape. I like it, but I've been studying chemistry for years, and it all just seems very obvious to me. But the fact that there is 1, 2, 3, 4, 5 pairs around that central atom says something about the shape that it's going to take. So, okay. Basically, after everything I said today, I could have given you questions: how many valence electrons does something have? But I think that's very obvious. The questions that I've given you, these, I think you can do them all. Let's look at those real quick just to make sure the backbone is going to be obvious enough that there's not going to leave you lost. 27, 28. Backbones here. I think I already did this one. pH 3. There's your backbone. Let me make sure these backbones are all obvious enough. And you will want to practice going through these and actually making the structures, because the rules get more complicated. And the structures get more complicated, and then the rules start to matter. We still have to do formal charge and resonance and stuff. It's just not obvious why these rules are used so good. But I do tend to want you to have the backbone rather than that be the thing you get stuck on. SCO2, there's the backbone. HI is just going to be HI. There's the backbone for HI. CH4, start with that for your backbone. NF3, there's your backbone for NF3. HBr, SBr2, S essential, C CL4. SF2. There's the backbone for SF2. SIH4. Start with that with your for your backbone. This next one, they give you a little hint for this one, C. Okay, so that's 29C. Use that for your backbone. 29D. For the backbone, use and just consider the C and the S, the central atoms. It's 29, look at 30. 30, I did this one on the board today, but C, 30 as C. That's 30. A, so use that for 30A. And the last one is, I think I did this one. 30B is, the C's are the central and the CLs are on the outside. So look at those and see, follow these rules and see if it makes sense. The expanded octets, I just think I need to give you a whole section on those by itself. I think you could do 32 or 33 as well. Number 32. Use that for A. The rest of them are just diatonic. O to H, BR to O, O to O. And then 33. Might have done that one. This is A, B, C. And that's D. So hopefully that's clear enough in the movie, in the video, unless you chose to write them down. Maybe you want to snap a picture of it. But having the backbones, then you can just step right into step 2 in that process, and you don't have to sit around trying to figure out what's the central atoms and what's the external atom. So those will help you practice those problems. You do those because we run into all the twists next, formal charge and resonance structures. If you took chemistry before, you will remember those words. All right, I think that's enough for today. You guys all right? I'll get your test graded as soon as possible. Any of you remember agonizing over number 29 on the test? I gave that same test in the afternoon. I did it twice standing there the other morning. Oh, no, the answer's there, it's good. And then in afternoon class, my SI, I said, would you double check that and make sure that's right? Because they were asking about 29 again too. And she came back and said, yeah, you're right, it's there. I did it one more time, and now I think y'all were right. Even though I did it twice, and my SI did it once. So the limiting reactant, I used the wrong one. I think I used the excess. That's what it was, right? And so another type, I found another typo too that nobody brought up. One question said O2, like what, you have this many moles of O2, and then later it said CO2 instead of O2. I noticed that one when I was looking at it. So tons of typos on the test. So I'll get them graded hopefully by Friday.
Will we like get points for those questions?
Huh?
Will we get the points for the questions?
Yeah. 29, I'll just give everybody the points. The ones I told you to skip, I might just eliminate altogether. Sometimes I use those as a curve and just skip right up. We'll see how the test comes out.
Thank you.